Hi there. Thank you for clicking on this video. Now, the title of this is When Students Ask the Tough Questions. And if I am perfectly honest, I am not exactly sure how this explanation is going to roll out. So I want to be honest about that. If you've got thoughts, comments, questions, feedback to give, I would love to hear it in the comments, what you would add to this or take away from it, or something that I haven't considered, because this was a question that has sparked some discussion over the last day or so. I want to give a shout out to my student. This was from a student of mine, Stephanie, who asked this question just yesterday in my math class. And what we were doing, we were looking at factoring quadratics of the form ax squared plus bx plus c. And her question was this: when factoring, why do we multiply a and c in order to look for the numbers that add up to b? And this was the key there, was the why. And if you're not familiar, depending on how you've been taught to factor, there's different strategies, but a lot of them involve the multiplying of the a and the c. So if you do the area model, which is how I teach my students, you do the a times the c. If you do factoring by grouping, you can do the a times the c in that strategy as well. If you've done something called slide and divide, you know that the first step in slide and divide is multiplying by the a and the c, and so forth. So it is a common first step. And in all my years of teaching, I'm not sure I've ever had a student ask me why, or when I said, well, it just gives us a bigger number, so we have more candidates for the factor pairs, like that, they weren't really okay with that answer. So kudos for the question, which then sent me on the, okay, in my head, I can kind of see why this is important. And if you've done algebra tiles, the algebra tiles give you a visual, and I'm like, I can kind of see it, but can I explain it? Can I justify it? Or am I even seeing the right thing here? And so this is where we want to go with it. So we've got the example 6x squared plus 17x plus 5. We're going to come back to this example. But what we're asking, like if you've done this on the area model, you've got the 6x squared and you've got the 5. And then the next step that we would take is we would do 6 times 5 to give us 30, and then use the 30 to break it down and find the numbers that would go into these two positions. And of course, like the student's question is, why? Like, why do we have to do that? Like, why not multiply by something else, or just pick a bigger number, or not multiply at all? Like, why do we have to multiply those two numbers together in order to ensure that we'll get the right pair? So what I want to do here is try to give a general idea of what's happening, and then look at a simple example to kind of see how the concepts are playing out, and then try to go back to that other example again. So if you've got, say, ax squared plus bx plus c, and you're factoring on the area model, okay, then we know that the ax squared goes in that upper left and the c goes in the lower right, because that is always how that works. And that by the time you get to this, that is a well-established fact pattern for how this is set up. Now, because this is an area model, the way we arrive at the ax squared is by multiplying the base times the height of that particular rectangle. And if you're doing it with the tiles, it'll actually be true to the area. Okay, when you do the generic rectangle, they all look like squares, but this holds for the area. Now, remember, if you multiply two things that give you a product, those are called the factors. And so essentially what you have up here, I'm just going to call this the first factor. Okay, so this is the first factor of ax squared. And then over here, this would be the second factor of ax squared. because that's how it has to be. Okay, you'd factor the x squared to get that area. And so you have the first factor and the second factor multiplying. Now, the same thing works for the c value. You would find the area of this rectangle down here by multiplying this base and this height, which of course would be the same as this base and this height. And so what we have going on there is we have, say, the first factor of c, and this would be the second factor of c. Okay, and what we have on the outside here now are factors of the ax squared and the c. Now, when I was taught how to factor, I was taught by like guess and check, and that's how we came up with the numbers in the parentheses. We would factor the first term, factor the last term, and then like check, because you would again be checking for that b. Like the b is always the issue no matter what method that you're using. Now, what that means is for our other two boxes, okay, what you're going to be doing is multiplying one of the factors of the c with a factor of the ax squared to get what is in this box right here. And so I'm going to try to abbreviate this. This would be the first of the c factors times the second of the ax squared factors. That's what's going to go into that box there. And then this one over here would be the first of the ax squareds times the second of the c's. Okay, so just so you kind of see what's going on there. Now, here's where we get into like why you have to multiply. In order to ensure that you are dealing with the right candidate numbers, you've got to have all four of those factors in play. Okay, if you only factored the c and you don't take the ax squared into consideration, you'll be missing these two factors. So if you look at this product right here, you need the first factor and the second factor of c, but you also need the first factor and the second factor of the a. Now, the x squared, you might be like, well, what about the x squared? Well, the x squared is going to contribute an x here and an x here. Like, we know that's how that's going to break down. And so that's why like it's the numerical part, the a and the c, that gives us that like the problem with the number part. And so in order to make sure that you have the right way to break this up and you get all four of those factors, what you've got to do is multiply these two together to get all four of those factors into consideration. So let's take a look at this example. We've got x squared plus 9x plus 20. Now this has the leading coefficient of 1. Okay, and then we have the 20 down here, and this one is simpler because you only have that 1 out in front, and so the only way for this to factor is to get the x times x. And then typically what we do is we take that 20 and we go and factor the 20 into all of the possible factor pairs until we find the pair that adds up to 9. And then that's how we break it up. And we say, okay, we have 4x and 5x. But I want you to notice what has happened here. What we've got going on is in these boxes, we have inherited one of the factors from the ax squared. There it is. The x and the x are coming in from the ax squared. And then the other pair are factors of the 20. And so you've got that combination of the factors there. And then when you go to get your GCF out, you see the factors there. And so what I'm trying to do here is show that these two boxes take into consideration this entire thing. So if you were to do this, looking for a different color here, to do multiply like right here, okay, that would be x squared times 20, which would give you 20x squared. And that would be equal to, if you were to multiply in that direction, would also give you the 20x squared. And the reason is because you've got to get all four of those factors, the 4, the x, and the 5. all have to be in play. And so in order to make sure that you are getting the factors that you need here, you've got to multiply these two together. You've got to make sure you grab all of them. Again, when you're only dealing with the x here and not with a constant out in front, you don't have a coefficient, then it becomes a little bit simpler. So when you come over here and you've got a 6, now you've got the factors of the 6 that are also going to come into play. And so when you're factoring this way, we've got the 6x squared and the 5. And what I know is like this is going to factor into a 1 and a 5. So we're going to have the 1 and the 5 in play. This, however, they could factor in like a 6x and an x, or a 2x and a 3x, and it might be in different places, but they are going to come into play because they are going to multiply into these boxes. So to make sure that I grab all of them, I've got to do, now you could do 6x squared times 5 and say 30x squared, meaning that these two would have to multiply to give you 30x squared. But we already know that the x's are going to be coming in from this. And so typically when we're doing the work, we only look at the 6 times 5 because the x's, like, we're reasonably sure we know like how that they're going to take care of, you know, themselves. And so now I've got to look at all the possible ways that might break down. Okay, and you could go through all of that, but we need them to add up to 17. So we know that this is going to be like, say, a 2x and a 15x. Now I am reasonably sure that I've got the products being the same. So 30x squared, and this will be 30x squared. So that means we've got all 4 of the factors there. And then we can use the GCF to grab the greatest common factor and figure out what these are going to be. And so we go ahead and do that, and then we can see that the factors are, be awesome if I wrote it down right, are 3x plus 1 and 2x plus 5. Here are the 2 factors that came from the 5. Here are the 2 factors that come from the 6x squared. You can see them with the areas here, and then they kind of get just jumbled up on the areas here, but it's the same factors in play. Now, I hope that was at least a partially decent explanation of why we have to multiply the A and the C in order to factor. And if you have thoughts, something you'd like to add, maybe another video to link to that would be a great illustration that would help me be able to explain this to my own students better, that would be awesome. And thank you for watching and hanging till the end.